Hi all. We have 3 viewers and 3 likes. I need at least 10 viewers to share my screen and do something. Okay. I need viewers, guys, to start. At least 10 viewers. Only then I'll start. Yeah, we have 10 viewers, 4 likes. Maybe I can start now. Right. No, it says 10. It says 10 viewers and 4 likes. Mm, I don't look good today. Some days I look good. Maybe I have to increase my brightness. It's all full. Yeah, bro. Granted my way into Apple by working so hard. You have to be grandmaster. At least you have to be international master to get there. Am I? So guys, so we have my stream again for a division 3. I haven't yet opened the problems. I'm proving you to people because all of you are scammers, right? If you're Indians, you're likely a scammer or cheater, whatever. So I'm just trying to show you that I'm not like you. It's not purple. This shade is purple. You see that, right? So now I will enter the contest. I don't want to see this number of solves, let's say for now, okay? Because in contest we don't have number of solves, right? Yeah, I do that. I said to my manager, but then wait, let's not talk about it at the beginning of the stream, okay? At the end of the stream, people don't. I can say whatever the shit I got, okay? Uh, so we are here, guys. Next rows, we have these things. We have F, G. What should I go with? What should I start with? Okay, we have many people solving till D. People are not even solving E. So I'll start with E. I'll read E. Okay. It should be very easy because it's division 2, right? Division 3, right? I will solve A2. Satyanarayana. It's not that difficult. A or E. Okay. A is your initial. Fuck. Okay, let me read E and F both. We'll read. How do we read this? We just read it from the very beginning. That's it. Okay. I know you guys can't read after this letter, but we can read the problems. Hidden knowledge of the ancients. Okay. It is said that the true power of the artifact can only be revealed in all sacred fragments. One minute. It's not opening. Let me open it again. So let me read the problem by then. It is said that the true power of the artifact can only be revealed by finding all sacred fragments, continuous segments of the tablet that contain exactly k distinct numbers. So, continuous segments of tablet that contain exactly k distinct numbers and their length must be between L and R. This sounds like a shitty problem. There's nothing nice in here, right? There's not nothing much nice. Okay, but let's read it again. A sequence A of length n and integers k l r. Given a sequence A of length n and integers k l r, you need to find number of such boundaries B and C such that, okay, we want number of segments such that among the elements this should have exactly k distinct numbers, and the length should be within this range. So how difficult can this problem be? This can just be some brute force. There cannot be some great idea or logic coming into here, right? It's just they asked you to do something, you have to do something. That's it, right? They asked you to do something, you have to exactly do this thing. You have to find number of such boundaries B and C. You have to just find exactly what they asked you to find, okay? direct, don't get scared of them. Like the video, guys. Yeah, you can say couldn't see how to count, but then it's probably brute force, right? I knew the approach, but couldn't fix left and properly. See, you have to have very much. You have to be clear first, and then you have to have optimism too. Let's try to see how I can solve it then. So we have this thing. So let's try to work on what does it mean, like exactly k distinct numbers, or let's try to fix c and then see how many b's are there for it. Okay, if you fix c, where are we? No. This is not it. How it works. I have to open a folder. Is it glitching? So let's fix C because there is no other way. Easy problem, right? Just think of a solution without fixing C. How would you count? Without fixing C. Just think of the other case. Without fixing C, would there be any other way to nicely count number of B comma C or B? Without fixing C or B, without fixing something, it would be much difficult, right? Like there would be no way c and b are equivalent, right? We can see from that side and all. So first step is obvious to anyone because without fixing c, let's say, how do you count? How do you count something great all of a sudden that it gives you directly this thing? Probably fixing c and then finding number of b's for this c and then adding up. That seems a bit simpler, right? Like otherwise how would you find? If it's not otherwise it will be a good problem. Because it's not a good problem, definitely you have to fix c, otherwise there is no simple solution probably, right? So first step is fixing c. We must fix c. You have to have very much confidence that it's definitely about fixing c. Okay, you have to have that confidence, otherwise it cannot be solved, right? Probably. So where are we again? So it seems simpler, right? Less than or equals to k minus less than or equals to k minus 1 is the answer. So where are we again? Okay, yeah, that's nothing but equals to k elements only, right? So we want number of, okay, if we know number of distinct elements, we can find the answer, right? If you know number of distinct elements, we can find the answer. So where are we? So we have to think. So there is nothing to think. Fix C and find the answer. Fix C and find number of B you get. So if you fix C, you know your A of C is here. Okay, let's use capital things. Until one number you have, first time you get, okay, and then if you keep going, and then if you keep going, you got first time k things here, and then if you keep going, maybe here you will get the k plus 1 thing. Maybe here you will get the k plus 1 thing. Okay, so if there is a range, there is a range for k distinct elements, right? There's a range for k distinct elements. This is simple. Why? You fix it C, you're increasing one element. After sometimes you will get k elements. If you keep going, number of distinct elements will only increase by adding new elements. And then if it is only increasing, that means there is a range for k. There is a range for k. And then we have another range. So there is a range for B. Okay. And we have another range for B. What is another range for B? L less than or equals to C minus B plus 1 less than or equals to R, right? That means B less than or equals to C plus 1 minus L, B greater than or equals to C plus 1 minus R. It's nothing but some lengths are allowed. If you fix this C, some lengths are allowed and you have some lengths are allowed. So you have to just take their intersection to find number of B's. So number of b's is just their intersection. So now, if someone can find number of distinct elements, the problem can be done. But finding number of distinct elements in a subarray is not that easy, right? In a subarray, finding number of distinct elements. Uh, if you can find number of distinct elements, you can binary search on k, where k exists, right? Where k plus 1 exists. Recently, I have seen someone's LinkedIn post where they were telling, given a range, find number of distinct elements in that. But then doing that would be more difficult. Like if you can get for some segment, then it can be solved with binary search. But I am very sure this is not the only solution. Okay, I'm very sure this is not the only solution. Why? uh, we only care about exactly k things. We can think of, if we have this range for if you have this range for AC, can I get it for AC plus 1? Can I get it for next thing? We can think of that question. Let's say we have those things for this one. Can now we get it for this one is what? Let's try to think of that thing. Okay. Or what else? Or how else can we do? Or because we want distinct things, right? We want distinct things. So so if we maintain if we maintain for each value, okay, it's lost index. See guys, you need not do these things because these things are for uh, many queries. If they are asking you random queries, l comma or l comma, then maybe you need these things. Okay, but if you are just doing something sequential, you can try to see what can you maintain and then how can you proceed. Why am I taking for each value lost index? Because that's what decides, right? The lost value will decide if that thing came or not, right? So for each value, let's say there is a lost index. Okay, this thing should be simple. This is not that difficult. What I mean by lost index, let's say you have 2 2 2 2 2, because we are coming from this side to see where is the first two. Only that one counts, right? Only that one counts. So you can do one thing. If you can keep lost 2 value as 1, if you can keep lost 2 value as 1 and remaining everything as 0, okay, if you can keep such a things, if you can maintain such a things, then you can, it's just range sum. Then it is just range sum, right? Then it is just range sum. Like now you can use Fenwick tree or something like that to get range sums quickly, and then binary search on that range sum and then do that. So we have one solution with stupid segment tree. We have one solution with uh, trying to maintain 1 in lost index. uh, Not stupid segment 3. We have a stupid solution with segment 3. When it's not needed, we should not use something big. Okay, it may scare away some people, right? This is not of a bad idea. Why? We only care about the lost index too, right? If you're coming from this side, if the lost index is the only thing that counts, that adds a new element, right? After that was added, this will not do any effect. So let's maintain those lost indices. Okay, let's say we have those lost indices, uh, let's say z, such that az equals to val, for all val, and then there is no, so z is highest such, highest largest z such that az equals to val. Okay, I mean lost z. So this is just that, right? We have two, and then z is that index. So then if we have these indices, we are interested in kth index and k plus 1 index, right? Why? If we have these indices in increasing order, kth index will tell first time k distinct values appeared. K plus 1 index will tell first time k plus 1 uh, distinct orders, right? Let's say you have this set in sorted order. then you can, if you can get the kth index, then you're good, right? So this can be one way. Can we always get whatever is the kth index, and can we always get whatever is the k plus 1th index? Guys, did my is my video there? See, E doesn't have any logic. Nice, Devil Itian. Yeah, I know that. I think it's his post. I thought about the solution a bit. I have seen someone's solution fine because they are using segmented, so it's not that great. I think the guy's solution was good uh, in the comments. The idea was will be used in many places, but if you leave that, we are here. If you can maintain this set, if you can always get the kth, I think why am I using sets? Because you guys need not know segment tree to write. See, segment tree for this segment tree is too much, I guess. Like right to find the number of distinct elements, right? Number of distinct elements. How do we do that? Number of distinct elements. Okay, that question was different. That question was if everything is distinct or not. Okay, that's an entire different question. Now I remember it. Well, leave that. We have this question. Maybe using segment tree also we can get number of distinct things, but no segment tree. This is bad. Number of distinct is definitely about the last index. So remove this thing. Okay, remove that thing. Number of distinct is always about the last index. It's about making this one, keep one here, keep zeros here, and then if you can get range sum, you can do. See, I like Fenwick tree. Let me use Fenwick tree and then just keep one here, keep zeros elsewhere. Learn Fenwick tree. Maybe I'll do a video on Fenwick tree if you guys want it. I don't have any enough demand to do things actually. Uh, so if you can maintain this 0 comma 1s for all values, then it's just range sum, right? So if I can use Fenwick tree to get that range sum quickly, and then I'll do binary search. Or if I can maintain, if I can maintain, shh, if I can maintain this kth indices things, okay. See, I will try to maintain. So if I keep one set for lost k things and another set for remaining things, can we get answer? So, but maintaining two sets is complex, right? If I can have these things, if I can have these things, what happens? One element will be gone, and then new element will come, right? Then what happens? One element will be gone somewhere, and then one new element will come. So, if it is going from the first k things, then we are good. Then we are good, right? But if it is going from the remaining things, see, I think if we can even have one set. If we know what's the value of this thing, of the k plus 1, then whatever you remove, if it is going from here, if it is going from here, you will remove the last thing and add it to here. Some guy can do with maintaining set pointers, this one, or I have to keep two different sets. Okay, if I keep two different sets for lost k things, I can remove from here and update accordingly. Okay, I can remove from here or remove from here also. I'll leave this question, guys. It's not a good question. Okay, it's a bad question. It can be done with prefix also, no updations. Guys, if you can have ordered set which gives us number of values above this thing, even then we are done, right? Hey guys, even with ordered set we are done, right? See, ordered set will give us number of values greater than idx. We do binary search on idx, and we do uh, we use ordered set to count frequency. Say guys, respond. I'll give more importance to people that responds. Is anyone here? Yash Mahota, are you here? So guys, why would I use Fenwick tree over ordered set? So why would I use Fenwick tree over ordered set? Because I know how Fenwick tree works, right? I know how Fenwick tree works. I can understand Fenwick tree. I have read it from CP algorithms. I tried to think of it on my own too, a bit. So I know how Fenwick tree works. I don't know how ordered set works. So I will use Fenwick tree. For you people, I won't even, because you people, I won't even use Fenwick tree template. I have Fenwick tree template, but I won't even use that. I will just try to write the Fenwick tree template, and then I'll just solve it. Okay. Fenwick tree template is so simple. It's just b of this equals to 0. Okay. And then void add of int idx comma int val, let's say. We want to add. So should I explain Fenwick tree? Guys, should I take this and explain Fenwick tree well? Tell me, or should I not do that? Okay. Even if I explain, the content goes waste, right? So yeah, I will explain Fenwick tree in most simplest terms possible. Okay, try to think of it. Try to think. We'll do it quick, but try to think. So think of think of an array. So guys, how can you store an array? How can you store an array is the first question, right? Uh, let's say you want to store an array. How can you store? What's the simplest way to store an array? If you store for each index its value, an array is stored, right? How was that? Is that understandable so far? For each index I, if you store a of I, then the array is stored, right? Hello. How to store an array? Yeah, you can store an array in that way. But is this the only way to store an array? What about this? What about this? Okay, if you store an array like that, if you store an array, I'll write it here. Fenwick tree explain. So now, yeah, no. What I mean was, like, mathematically, if you store a of I equals to I, sorry, if you store an array b of I equals to a of I, okay, you want to store array A, store array A. Let's say this is just a number of elements. If you just store this one, you have the array. Now, if you want to, up, if you are storing the array in this way, if you want to update an element, update an index I, how long will you take? This is first question. Okay. Second question. So store means you're not storing anything else. You're only storing these things. If you have to get sum of a range L to R, how long will you take? Because you're not storing anything else. You are just storing these things, and now you are asking L of R range. What is the sum of this range? So I want answers for this and then answers for this. Give me complexities for both of them. It's going good only, bro. Respond, guys. Well, this is the way you are storing the array. Then after one update, you can update just one value, right? Because you're just storing that value, so you can update that, right? So what is this one? Is this O of 1? Guys, answer please. I'll end the stream. I am almost fed up with these streams. Hello, why can't you guys respond? Just yes. Okay, you guys can't chat while saying. Is it difficult to chat while saying? There is no B. See, what I mean by B is, Aryan. What I mean by B is I'm just storing A of I value in the array. I'm just storing A of I. That's it. Nothing else. For array A, I'm just storing A of I. Nothing else. I'm just storing A of I for array A. Nothing else I'm storing. For each index, we know A of I. Then this is O of 1, right? Updating that. I'm explaining Fenwick tree, bro. Just respond properly. I'm trying to explain it in my way, okay? Uh, so if you are maintaining this thing, if what you are maintaining is this, okay, then you can update one element in O of 1, and you again have what you are maintaining for the new array, right? You can update one element in O of 1, and then again you have again you have what you are maintaining. What you are maintaining is just the array you are maintaining. You have this for new array. So let's say instead of maintaining an array ai, if I maintain b of I equals to sum of 0 to I, if I maintain this thing, okay, if this is what I'm maintaining, can we get the array back? Yeah, we can get the array back, right? If you subtract a of this minus a of b of this minus b of this, you have your a of I. So if you are maintaining this thing, now the same questions. How long will it take to get a sum? Answer this one. It's O of 1, right? You can just do B of R minus B of L minus 1 to get the sum quickly. This is not difficult to see because this is 0 to R. This is 0 to L minus 1. If you remove that from 0 to R, you get L to R, right? So this, you're able to get sum quickly. So do you guys see that? It's not needed. I'm just explaining. Maybe with sets it can be solved. Maybe there is some other solution. But when you are getting some content, when you are getting explanation for Fenwick tree, take it and try to focus. Okay. The fuck, viewers are dropping. I am getting very irritated these days. I should not be like that. I know girls have those mood swings and all. I should not be like that. I know, but my jaw is paining. I got some jaw pain, uh, and I got it while doing stream. It became more actually one time. Uh, so here, how long will it take to update? So, how many elements are changing in B? Right, that's what we want. When you update A of I, if you update A of I, all J greater than I will change. Right, this is O of N. Do you guys see that? Do you guys see the difference between this and this? Okay, I got it. This is without fixing C, right? So that would be without. Okay, that's a nice question. That's a nice thing. I got the solution that Mohit told long back, but let me explain Fenwick tree too. Okay, if you break down it like that, now what do we want? Now we want all subarrays that use us, but even that is not that easy to count, right? Okay, I'm just trying to explain Fenwick tree. Uh, so this is how I'm explaining Fenwick tree by telling to consider an array A of I and then trying to consider prefix array. Okay, if all you're maintaining is this array, then what happens is you can change an element in O of 1, but to get the sum, you must do O of n. Okay, but instead, let's say you're maintaining prefix sums. Now, you can get the sum quickly in O of 1, but to change an element, you have to update all the indices that occur later, right? Because all of them will be updated now. Why? Because that's what you're maintaining. If you're maintaining something, and if all of those, if this is what you're maintaining, and all those indices are changing, then you must update all of them, right? Because here the constraint is this is what you're maintaining. So now, what is a natural question that may arise? Okay, from complexity wise, what's a natural question that may arise? Can you maintain something else that gives you that gives you both in what complexity? Hello. So we can think. Do you guys see between prefix sum and normal array? Let's say prefix array and normal array. If you're maintaining this, then sum will take O of n, but update will take O of 1. If you're maintaining this, sum will take O of 1, but update will take O of n. Okay. Maybe there is something. So if you notice this thing, this is also uh, sum of this is also a of I to I, right? This is also a of I to I. This is a of 0 to I. Okay. Maybe if you generalize this, I'm explaining from CP algorithms maybe to something like a of, let's say g of I, comma I. Let's say you're using this function g of I. Instead of using 0, let's say you're using something else. Because if you're using 0, then it is prefix array. If you're using I, same value, then it is this. Maybe if you use something, if you so what does this mean? Range is I comma I is normal array. Range 0 comma I is prefix array. B of I equals to sum of. B of I equals to sum of. Maybe there is something. If you generalize this a bit, what you get? B of I equals to sum of some G of I, let's say. We don't know what is this function G. Let's say this one. Let's say this is what we are maintaining. Can there be complexity of O of log n comma O of log n for both operations. This can be a question. Why? O of 1 is too quick. O of 1 is very quick than log n. You guys may think log n is small, but think of log n. Log n grows exponentially, right? Not exponentially, log n grows much bigger, right? Log of 1 crore is 1 crore. I mean, very big. But log of 10 power 1 crore is 1 crore. But then O of 1 is just O of 1. So with respect to O of 1, log n is very big. O of n is even bigger. So log n is something in between. Can we do something so that both of them can be O of log n and O of log n is a question? Okay. Bro, it is prefix array. Okay, this is prefix array. See, this is prefix array 0 to I. And okay, try to focus here a bit. Okay, I know you came late, but this is prefix array. Is that clear? Pradeep KR. What do you mean B? Can't you even type more so that it will be more more I can understand it in a better way? I wanted to say if all you're maintaining is this one, then what happens? So now maybe we can think of something. Okay, something. So it is about what you're storing. If you're storing these summations, you're getting that. If you're storing these ones, you're getting that. But there is something. If you store some other ranges for each I, maybe then you can do both of them in O of n. Okay, maybe then you can do both of them in O of n, O of log n. So this seems a question, right? Because one is, do you guys get my generalization a bit? Guys, I'll end the stream if you guys don't respond at all. Yeah. The fuck you mean some range you get used in segment tree, right? Bro, I'm explaining you theory. Okay. If you came in between, try to watch the video before. What I'm explaining you theory is, let's say all you're maintaining is this. All you're maintaining is A of i's value for all I. Then to update one index and get again what you're maintaining. See, I'm trying to explain you people good logic to think of what you're maintaining and then how to get it back. But then you guys will say random things like for range you can use segment tree. The problem is as simple. The problem can be explained to a sixth grader. Okay, no knowledge is needed. What am I telling? If all you're maintaining is an array values, then to get the array values again, if you have a of I, only that is getting updated. So update is O of 1. But if you have to get some, there is no other way because all you're maintaining is array indices. You have to go and then you have to add them up and then you have to get them right. In segment tree, you are maintaining some big segment tree, and for each segment you are maintaining its value. Because of that reason you get that. But then if all you're maintaining is just array values, you cannot use segment tree here. Why? All you're maintaining is this. Then I'm asking the question, okay, then some will become O of n, some must become O of n. But if all you're maintaining is prefix arrays, then you can do both of them in, you can do this in O of n. If all you're maintaining is this, you can get some quickly of a range. But then once you update A of I, all this B of I will get updated, right? Why? All of them include CFI. So all of them must be will change now. So you have to update them. You have to touch all of them. Okay. So this is often. Do you guys get now? It's not for experts. Okay. I'm explaining it for newbies. I hope you try hard. Okay. Once the video ends, spend 2 hours, play the video, slowly watch, slowly think, slowly try to understand. Okay. Try to use it in that way. Newbies and higher people is they use what they you have well. So if what you have is, it's contradictory. If you cannot use what you have well, So you get it right. So now naturally a question comes, some range, some other range that gives you both in off login, comma off login. Okay. See, what I'm saying, if you understand it, it will be, because I'm repeating so many times. But if you completely ignore it, if you completely don't try to understand it, everything seems complex. Okay. If you try to understand it, maybe after trying 3 times, if you get it once, the question, if you are maintaining this, then you have to do, not that is difficult, right? What the fuck is, just because I'm making things a bit logical. These things. Now the question comes: if can you maintain some g of I that gives you both in O of log n is a question. Do you guys get that? Do you guys get that? So now we have array. Okay, for we have an array A. Sorry, we have an array A. Okay, we have an array B. If we maintain for each index I, if you maintain these ranges, for each index I, if you maintain these ranges, if you maintain the entire range, then once this value gets updated, you have to update all these segments, right? Because all of them are getting updated now. But if you just maintain these values, then what happens? You can update one thing quicker, and still you will have your data structure. Data structure is whatever you're maintaining is called a data structure. Okay. And but some, because all you maintain is independent values, you have to touch all of them, because unless you touch this, you don't know what is there, right? Right. So you have to touch all of them, and then you get the sum. Now the question is, can there be some ranges? Can there be some ranges? Let's say for I, you don't store just till here. You don't store till here, but you store somewhere in between. For each I, you do something like that. Okay. Now can you do it quicker? Let's just see g of I equals to n I by 2. Let's just try to see this thing. Okay. If you see this thing, what does this mean? For I, what you will store is I to I by 2. You will store for I to I by 2. Okay. So now, once you update I, what all will be updated? Everything that falls here will be updated. Let's say you're updating mid. All of this must be updated. That's again often. So this is not good. Now, now again, update is often. Okay. But can you get some quicker here? Can you get some quicker, guys? How? Let's say you want sum of 0 to I. Okay, you're at I. Now you can go to I by 2 quickly, and then you have this sum. And then from here, you can again get the sum quick. And then you can, from here again, you can get the sum quick. So sum can be done in log n here. Sometimes it's often. When I equals to mid n by 2, let's say, we must update all I such that I by 2 less than n by 2 less than I, right? So which would be I less than n less than, we have to probably update all of them. Okay, all of them. Sorry, not this one, but let's say you have mid by 4 or something. Let's say you look at n by 4, I by n by 4. Okay, now it is I less than n less than n by 2 less than 2I. Or if you see it in some other way, I think you can see all this range will include, this will include this value, this will include that value, all of them will include that. Sorry, I equals to n by 2 itself works, all of them will include that. So sometimes you have to update all of them, right? Did you guys get what happens with g of I equals to I by 2? if all we maintain is b of I equals to sum of a of I by 2 comma I. See, you guys should understand the difference between my explanation or somewhere else you learn is once you learn from me, you will not forget it, most likely. You will remember it and you can probably implement on your own too because learning in a nicer way takes more work, takes more effort, but then you will do well in the future if you I mean you can do well in the so one thing we can try to think of is can we maybe use some bitwise uh, representation to attain both. Let's say we want to use some g of I, some bitwise functionality to attain both. So what I mean here is we what do we want given any index I, okay, or let's say we will go and find g of r, okay, we will find g of r. So now we have this sum g of r to r. Now we have to go to g of r minus 1. So I will write the code already. Some code seems simple, right? uh, int sum of int r, let's say prefix sum. What should we do? For int r I equals to r, I greater than or equals to 0, red plus equals to b of I, and then what should happen to I? I equals to g of I minus 1. Am I correct? Return sum. Is this correct for return red? Is this function correct for returning sum if all we are maintaining is g of I to I? Is this sum correct, guys? Is that sum correct? Hello? Do you guys get that? That some code seems simple, right? Some code seems simple. This chat is not going down now. So this sum code is clear, but let's say add. What about update? You should update all j such not equals to I less than or equals to j. This j you have to update. Am I right? If you are all we are maintaining is those segments, if we must update that segment. So now we know what is our goal. We want some ranges for any r. They quickly go to 0. In log n, they have to go to 0. When you do g of r minus 1, when you do g of r minus 1, or from r you come to g of my r minus 1, and then you go to here. Something should decrease quickly so that you go here in log n, and then you can get some quick. And another property, take any I, number of things that fall on it. Also, this number should be small. So we want two properties to hold. I2 g of I, I2 g of I minus 1, 2 g of I minus 1 minus 1 up to so on. This should compress quickly. And given an I, number of things that fall on that, that also should be log n. This is what we want now, right? Do you guys get it? Do you guys logically get what I mean? Say yes, even if you don't. Because the question is, if you are maintaining these ranges, then to get sum quickly, what do you want? You want those ranges to go quickly to zero, right? If you're doing g of I minus 1 up to so on. But what about update? For any I, number of things that fall on that should be small. These are the two constraints you want. So we are trying to find some functions based on bitwise representation. Okay, we are trying to find some functions based on bitwise representation. So let's say we have, I'm not explaining this well, I'm trying to end the stream quickly. So let's say we have something like this. uh, Let this be I think if I write a function based on this number of bits, like somehow if I use some bitwise things and then make number of bits smaller, once I go to g of I minus 1, once I go to g of I minus 1, if I can make uh, some progress, like if I can make some progress, okay, in terms of number of bits, like let's say number of ones reduces, then as we go from here to here, number of ones reduces, then we will quickly go right to zero. So can we find such a thing? Can we guess such a thing? If you think of that, I think one thing is, let's say for these things, if you remove if you remove lost ones, if you remove lost few ones, then what do you end up with? If let's say g of I equals to removing lost few ones, okay, if g of I is removing, I'm guessing that now, if g of I is removing lost few ones, what will happen to g of I minus 1? What will happen to g of I minus 1? All of them will become ones, okay, and you will have 0 here, and then you will have 1 here, up to so on. Is this progress? You have two ones here, now you have more number of ones. For sure you will have more number of ones, right? Why? This 0 became 1, so now we have more number of ones. If you are keep going like this, wait, what happened? This will become 0, okay, this will become 0. You'll have more number of ones, and after some time, wait, I am not getting. So from here you are having more number of ones. Maybe if you look at g of I think something else is reducing here. If you see that, let's try to see that. See, some leading bit has been reduced, right? Some leading bit has been reduced. So this leading 1 has become 0. So that leading 1 has become 0, and then we have all of these as ones. If you again remove these ones, and then if you do it again, now what happens? All these ones, removing all these ones will make it more number of zeros, and then you have 1. So I think, I don't know if this is the g of I used in Fenwick tree, but this seems to be working, right? If you remove lost ones in g of I reduces, and then whenever you do minus 1, it seems like a progress because you're merging this one with the number of ones now, and then once you remove them, again you're removing more number of ones. So now there will be some other one here, so now that will get merged. So we can see that some new one is getting merged here. So when all the ones will get merged, when you do g of I, it will become 0. And we are always coming smaller. Maybe after some time, you will have some number of ones like this, and then you will go down directly. Okay, once you reach the most significant bit, you will directly go down. You will reach this one, this being 0, most significant bit being 0, and then once, and then you will directly go to 0. So we can see sum is reducing quicker in here, right? Yeah, that's an idea, right? If you maintain root and size segments, then what happens? Then you have then you can do both update and sum of any range in root n, and that's square root decomposition for you. See, do you guys see that? Pradeep, KR root n idea is a good idea. That's square root decomposition. See, maintaining that. Now number of things you have to update is root and things, right? So that's actually good. So if the question was you have to use fixed length segments, what's the best you can do, then root n is the answer. Do you guys see that? If the question was you must use fixed length, then root n is the answer. Because with fixed length, you cannot do better than root n, right? Either this will become more or that will become more. Now, now we are trying to use somehow bitwise operations. This I'm guessing. Let's say we are using bit. I'm not doing that well because it's let's say this is our guess. This guess satisfies removing large number of zeros, and then when you do minus ones, this one will get merged. That one will become zero, and then you will have more number of ones. See, we are removing this leading bit. Let's say this is our function g of I. Then this goes to zero quickly, right? I g of I minus 1, g of I minus 1 minus 1, base 2 representation of I. I'm trying that because I'm trying to use log n, right? So I'm thinking maybe g of I will use some bitwise operation. It will manipulate those bits to uh, find g of I, is what I'm thinking. We're trying to guess that. So if I guess this one, like if I guess like removing last zeros for g of I, and then g of I minus 1 should show us some progress, right? Then g of I minus 1 will be, it's actually showing some progress. When you do minus 1, now all of these are zeros. When you do minus 1, this will become 0 and all of this will become 1. So next time you do g of I, all of them are 0 again. So number of zeros after you apply g of 1, g of I will keep increasing. After you apply g of I, number of zeros will increase. Once you apply g of I, let's say these are number of zeros. The next time you apply g of I, this one will also be 0, right? Because when you do minus 1, all this became 1. And then when you do g of I, all this will become 0. So every time you're doing g of I, number of zeros are increasing. So number of zeros finally will become all 0. Then you have your whole array in just log n steps. But I'm not very sure if this itself is Fenwick tree, g of I. But now we have to think of this case. If you have I, what all j will fall on this? You have to think of this thing well. Okay, guys, are we here? Do you guys see this? See, value here. You guys don't get the value of thinking this much. You guys don't see the value. That's Indian mentality for you. I don't know why. Like you want to know what you are getting before putting some effort. I don't see why you guys do that. Like you have to put effort sometimes when you, even though you get nothing back. Okay, if you can't do that, yeah. So now we have to think about that, right? We have j, we have I, g of j. What all j involves I is what we want, right? Because g of j is nothing but removing lost ones, right? So this is wrong probably. Why? Why is this wrong? Okay, no, this may not be wrong. J J falls on J falls on these values. J falls on these values, right? J falls on all these values. Okay, this is can be more. J falls on more, but then our question is number of things that fall on I, right? Number of things that fall on I. is our question. Okay, let's try to think about this. Nice, Nirmit. So leave the square root, Pradeep. We are now trying to look at this g of I. Okay, we are trying to look at removing last one's g of I. Okay, we're trying to look at removing last one's g of I. If g of I is removing last ones, what all j will fall on I is what we are trying to see. What all j will fall on I. It doesn't seem that simple, right? Why? For what all j will this fall? But one thing can be clear, maybe. Let's say you have 1j. Let's say you have 1j. Okay. Let's say you have 1j for which removing last ones, removing last few ones. So we have j, right? We have to use j greater than I. Okay, let's say we have I here. We have I here. I would be I bitwise representation would be 101. I should get some iPad, I guess. I'm not having I used to have my friend's iPad with me, that's why I never bought it, but how to get iPad, I guess. Or I have to quit streaming. Either one will work. So let's say we have this to be our I. Let's say this is our I's bitwise representation. Now what one thing we know is j greater than I. J greater than I means you have some prefix matching. Okay, and then you will have a 1 here. You'll have 1 here when there is 0 here. Okay, you will have 1 here when there is 0 here. So what it means that after you remove these things, after you remove last few ones, this should become smaller than or equals to this one. So if you see that, if you see that if j is if j's 1 is here and if there is a 0 here, removing last ones will not make it smaller. See that? See guys, for all the j, see we have, so I think this is the solution. Because of this is the solution. Do you guys see that? So I remember g of I to be this one. So we got g of I, and then this g of I is working well. Okay, number of, see, let's take our time, because this idea of 1 greater than 0 is used in many DP problems, many brute forcing bitmask DP problems, everywhere it's used. So keeping some time, looking at this, thinking a bit, all of these things will help you. Okay, believe me, because I have done all these things, right? I don't even have any rating. I don't even have, my rating is 2100, but I have done all these things. So you guys should also be trying those. But I have done even. If you check out my last stream, even was simple to me. So guys, do you see this? Number of ones at last. See, ask doubts. Okay. Number of ones at last will change. So for g of x, number of ones we remove will be difference. You mean you mean x to g of x length you're talking about, right? Yeah, that's correct. That's correct. But now, Joy Kanna, what we are trying to see is what all j will fall on I. What all j will fall on I. So j greater than I. Let's try to logically apply that. See, whenever you're proving things, whenever you're trying to apply questions, use questions, solve problems, you have to think, am I using what I want? Am I using what I want, right? Because I have to use j greater than I. So I'm trying to use j greater than I logically. Now if I write it like this, now I'm using that j greater than I. Okay, so if you don't use that logically, you're never solving the problem, right? Do you know what I mean? Are you guys getting what I mean? This same thing may happen to you in problems. Let's say there is something told about something, but then you're never using that logically. You're saying something else. You're never using that point. Then you cannot prove it. You cannot go anywhere, right? Do you guys see the importance? So now we are here. So j greater than I means some prefix will match, and then you have 1, and then you have 0. Is this clear, guys? Is this clear? Is j greater than I clear? Is j, does everyone agree with me about j greater than I bitwise representation? You guys agree, right? If you guys were asked like 932 rupees and 432 rupees, what is bigger, what will you take, you will see from the beginning, okay, 9 is greater than 4, so I will take 9. So if something is bigger, that must happen some at some higher power, right? Highest power pays lot more weight in all bitwise representation. Some prefix may match and then the next highest power will matter. So now after removing these ones, okay, after removing these ones, if it is becoming less than or equals to, if there is a zero, it will not become, right? Answer me. Now we have some one, zero. If there is a zero after this one in J, will G of J becomes less than or equals to I is the question. Think of that. See, if there is a zero, last ones when you remove, this one will not get affected. So it will not become smaller than this. See that? I'll get some water. Sir, I wanted to tell you, actually one day, 2 days, I guess. I just got curious. I was hungry to suggest to them. Uh, Joy Kana, Pradeep KR, is there Eshmahota? Eshmahota, are you there? Okay, I'm moving my left. Le- Priyank Bist, I'm explaining Fenwick tree in my own way. Okay, so we are not solving any question. I'm explaining Fenwick tree for no reason. Okay. No, it's not about question. It's about explaining Fenwick tree. Is this clear, guys, to everyone? Uh, Pradeep, did you understand that if there is a zero here, you are only removing last ones, right? That's your g of I. If there is a zero somewhere after this, then j will never become less than I. Then g of j is greater than I. Is this clear? So, so let's look at j comma I, j greater than I, and let's call bit x where j greater than I for first time. If there is a 0 after this bit in j, then g of j greater than I. The question is too long. 99. So to my viewers, now we are interested in g of j less than or equals to I, right? We are interested in these things, right? So what does that mean now? What does that mean? This happens only when all of them are ones, right? That happens only when all of them are ones. So if it is happening only when all of them are ones, how many such j can be there? J greater than I, if prefix matches here, only when all these are ones, you have that j. Because all of them are ones. So now we don't have many different things because all of them are getting characterized by the first bit greater than 0, right? So you have log n such possible j's. Do you guys see that? First, what we have seen was going from I to g of I minus 1 up to so on is log n progress. And then we are trying to see, we have seen that number of j for which this falls are also special. It's take I, keep adding ones, keep adding ones, keep adding ones, right? Take I, keep adding ones. Whenever here is 0, because all of them are having suffix ones, right? And then whenever this is 0, this is 1. And then again same. So what is it like if you have I? If you have I, if you have I, it is just keep adding ones. It's just keep adding ones. Whenever it is 0 and you add a 1, then that one will come down. Else it won't come down. Right? Make a 0 as 1 from behind, then j is greater than I because a 0 became 1. But then you remove all the ones, so then it will become lesser. So it is about making this 0 1, making this 0 1, and then making this 0 1, and then making this 0 1. These are the j's that we have to worry about. Is this clear, guys? uh, Bro, don't irritate me, okay? I'm not explaining ye, I'm explaining Fenwick tree, okay? I don't know why you people are like this. I'm explaining Fenwick tree, okay? So see, okay, I got it. You might have thought I'm explaining E. I can totally understand you, but I'm explaining Fenwick tree. So see from the beginning, okay? Later, see later, see later. Okay, it's fine. See later. I will change the title to Fenwick tree explained beautifully, okay? I can say whatever I want, right? So, guys, do we have how many followed from the beginning? See, no doesn't mean anything. No means they came in between. But S means they have followed and they have understood. It's just six people. With very low viewers, I'm giving out premium content for free. I don't know why or how am I doing that. It's premium content. At least I like to consider that it is. When there's no one around. Nirmit, have you understood? What about Nirupam? Guys, like the video. So now we know how to go to G of I, right? We know what is G of I, removing lost ones. We know how to find all J's where I comes. It's just making this 0, 1 and then making that 0, 1. Do you guys agree that? I will just teach you two people, okay? See, guys, if I ever try to train some people personally, I will do that to most active people, okay? Rather than a course. Nirupam, which bit part? How they go to 0 quickly, or how only few J's exist for one I? Please respond quickly. So after that, the problem is now you have this function. We are trying to analyze this function of removing few ones. And then we are trying to see to update. See, to update I, if I is getting updated, let's say if I is getting updated, you have to update all the segments that fall on I, right? All the segments that fall on I you have to update. So we are trying to count that set. We are trying to count this set for update. We have to find this set j such that g of j less than or equals to I less than j. You have to find this set of j. To do that, because I let's see, if you write mathematically, because I less than j, we're trying to look at bitwise representation of I, we're trying to look at bitwise representation of j. Here is 0, here is 1, j greater than I. First time this have happened. Now if there is a 0 here, after you remove lost ones, it will not become less than. Just all you have to see is that just this one point. You have to understand this one point, okay? If you understand this one point, you can see all of them must be ones, and after that this will become less than or equals to this. So if you see that all of them must be ones, and then this is equal, so you don't have more possibilities, right? For j, all of them are ones and then this is matching. So what is it like if you have bitwise representation of I? All of them must be one. Like it's like all of making all of these as ones, making all of these as ones. Those are the only j's that are possible, because they have to end up with all of them as ones, and then prefix should match with I. So some prefix matches with I, and then everything is zero. Everything is ones. These are the only J's that come. So if the J's are prefix matching with I and then all ones, how many such J's can be there? How many such different J's can be there? Prefix matching till here and then all ones. Prefix matching till here and then all ones. Prefix matching till here and then all ones. These are the only possible J's right now. Because if there is a zero, it's not possible. J will not become less than or equals to I. But if all of them are ones, now what is this? Prefix matching with I and then all ones. How many different values you can have? Login. So guys, now we are very clear. Now we are very clear about how to get sum. We already wrote our function how to get sum, right? Which is trying to go from I to g of I sum is in here, and then we have to go to g of I minus 1. Getting sum is clear. How is getting sum? People who following, it feels like I'm going very very slow, right? But people who are a bit troubled, I'm trying to clear that. So when we are at R, we have to go to, when we are at R, we have to go to, so R to G of our sum is in B of R. After that, we have to go to G of R minus 1, because this is G of R, we have to go to G of R minus 1. So we went to G of R minus 1 after that. Okay. Is sum clear? And or is how to find J's clear? So now let's try to simplify the code. How to remove last ones? How to remove last ones? Last ones means here is zero, here you have ones, right? How to remove last ones? Any idea, guys? How to remove last few ones using bitwise operations? See, we have already constructed G, right? Logically, removing last few ones is our G. G of I is removing last few ones. That's it. Okay, Pradeep, that's clear, right? Mm, yeah, this is one formula, but we can do even better bitwise operations. How? If you do plus 1 to this, what happens? If you do plus 1, if you do plus 1, what happens? This 0 will become 1 and all of them will become 0. See, what you have given me is nice. That is correct. This is correct. As long as there is a 1, keep removing. That is correct. But then again, you have to extend, right? Again, you have to extend. So, if you see these two things, I and I plus 1, using I and I plus 1, can you tell me something that makes all of them as zeros? Is there something that makes, uh, because this is already 0, all of them as zeros? If you have I comma I plus 1, why? 0 1 1 1 is I, then I plus 1 will be, these two are same, common things. They can be anything. Okay, they can be anything, common. I plus 1 will be, this will be 1, all of them will be zeros. That easy to see, right? 2 power n minus 1, 2 power n, 1 plus 1, 0. Carry, carry, carry comes here. So using I and I plus 1, is there some bitwise thing you can do to get all of them as zeros? Answer me this. You want all of them zeros, bro. You have 1 0 0 1 1 0 0 0 1. Try better. Guys, Nirupan, also you try. Joy Kanna, also you try. What happens if you take and? Will these things remain same? Yeah, those things remain same. And then all of them will become 0, which is nothing but removing last few ones. So G of I is beautiful now. So, so what we worked on is removing lost few ones as our g of I. Lost consecutive ones, contagious ones is our g of I. And we clearly proved that g of I minus 1 goes to 0 in log n steps. And we clearly proved that set j, g of j less than or equals to I less than j, this size is less than or equals to log n. We clearly proved these two things, okay? We clearly proved these two things, right? And what is g of I? We also showed that g of I is just I and I plus 1. Just g of I is just this one. So where are we, guys? J. My jaw really hurts this side. Guys, so have code for sum. So let me talk by then. Let me just talk. So guys, I'm just talking. Okay. Uh, why is that clarity that bad? So see, what am I talking? We have a way to go before. Jay Patel, I hope you can follow it later. Okay, don't see now. We have to see from the beginning, I guess. You cannot see from middle. I think it's bad if you see it from middle. It will be like spoiler. Don't see it from middle. Okay, guys, don't see from middle. Uh, I think it's back. It's back. So guys, don't see it from the beginning. Okay, don't see it from the middle. Jay Patel, I will, because it will be a bit of spoilers. Okay, so something. Yeah. So change my Wi-Fi to just some other Wi-Fi. So guys, before there will be more gap, let me explain it. Okay. So now, so now agree that we have code for sum, right? So we have code for sum, right? Fall on I. It's making seems we are good now, at least a bit. Right. So now what about Jess? What about Jess? It's like, what about Jess? It's making lost zero as one, right? So let's say you're till here. Let's say you're till here. Let's say this is your I. Okay. Let's say this is your I. So what are all the J's possible? You made all these as ones. Now what is it about? You have to make this zero as one. So previously it was making all these ones as zeros. Now it is about making this zero as one. How do you make this zero as one, guys? How do you make this zero as one? Any idea? Any idea how would you make that zero as one? Given given I, you did remove lost ones by I and I plus one. So if you do plus one, what happens? This will become one. All of them will become zero. Okay. But we want all of them to be one. We want also this to be one. We want all these things to be one now. So how would you do that? Yeah, we can just do or. So after doing or, you will go to some new j. Now from this new j, you have to again find the next zero, make it one. So from this new j, you have to keep on doing that process. If there are multiple ones, all these ones are fine. Now this zero should become one. See, even after there are some ones, all of them ones are fine. Now we are targeting this zero. We are targeting this zero to make it as one. So we are doing good. We are doing correct. We are doing correct. We are making all the j's. See, we have proved there can be no other j. All the j's are of this format, and then we are covering all of them, making this zero one, making next zero one, making next zero one. So to make from behind lost zero one, what we have to do? We have to we can just do whatever the current j is, we can get the next j by making that 0 as 1. So whatever the current j is, by making the 0 as 1, you can make the next j. So Finding all these j's also seems simple, right? So what about these j's? So union I. Okay, we have this union I. I also falls on it, right? So let's start with I. IDX. Int I equals to IDX. Okay, I equals to IDX. What we have to do? We have to update b of I plus equals to val. And then what we have to do? I equals to I or I plus 1. Return. Done. Is this correct, guys? So I think we can even remove this thing. Why? We have only IDX, right? We can just keep IDX. We are beginning with IDX. We can just change that value. So even this would work, I guess. Right? How can we further simplify this? Maybe or equals to I plus IDX plus 1. What about this one? What is this one? Or and or plus 1. Right? So can you guys write Fenwick tree code now without copying it? So this explains why I don't use ordered set when I can use Fenwick tree. Even if it means to reindex numbers, reindex numbers, I prefer Fenwick tree somehow. I mean I use set when I don't know the inside functionality of red, blue trees, balance the trees, rotate them. I don't know that, but I still use set. Mm, so guys, see how was my explanation? Can you find better on YouTube? It's intuitive, but it's also a bit more mathematical, right? It's also we came from, is there something in between? O of 1, O of n, O of n, O of 1, is there something in between? We tried looking I by 2. Maybe this I directly told you guys, but still we tried seeing that, okay, removing last few ones, you remove last few ones, more zeros, minus 1, this becomes 0, and then more ones, and then again remove last few ones, now even more zeros, do minus 1 and then remove last few ones, even more zeros, even more zeros, you'll go to 0 in log n steps. It's not just intuitive, it's a good explanation, I guess, right? Like, it's, see, the thing is, you may not forget this that easily. We are proving clearly, right? Overall what we are doing, we know very well that if we are just maintaining those segments and then we are updating all those segments somehow. See, if you think about it now, you're just maintaining some segments and then you're updating those segments and then you're getting those segments some too. So what you're maintaining is some special segments are there, and you store b of I to g of I to here. Yeah, logical, intuitive, and everything, whatever you guys can call it. Comment in the below that later of the video, comment that okay, this was the best Fenwick tree explanation I got. I will never forget this or anything. Lies. Just say lies. Okay. See, not even that. We know this way of storing. Everyone knows this way of storing. And then we know this way of storing too. Here you get update quicker, some lesser. Here you get some quicker, but update takes more. Logical question, let's say, of someone might be, okay, can we do both in overflog? And let's say someone is researching this, then they would think, okay, can we do both in overflog? And they might have thought, right? So now we know Fenwick tree, right? So that's it, Fenwick tree. Another function can be int sum of L comma R. Return sum of R minus sum of L minus 1. So if L is negative, we will return 0. So it is fine. If you see Fenwick tree template 2, what is Fenwick tree template? Return 0. R greater than or equals to 0, R equals to R and R plus 1 minus 1, return bit of R. It's called binary index tree. Complex name to remove last few ones and then maintain some segments. Right, same. What is add? Add is this one. We wrote even better. But then we have to do I less than n. Sorry. Or else you keep going, right? Because of this, you need some size, big N, maybe capital N works or N works. And then I have to keep N here instead of below. Was it behind sounds? Why are you guys laughing? So I'm ending the stream, guys. Bye. So I will solve E here and then I will end the stream. I will use Fenwick tree to solve it. Okay. So I will use our Fenwick tree to solve it. Let's call it bit for no reason. Binary index tree. I don't know why it's called binary index tree. Binary index tree. Tree. How is it a tree? Maybe there is something we are missing here. Maybe they form a tree. I think they form a tree. That's why it's called binary index tree. Some J to here, maybe they will form a tree. So even after this explanation, maybe we are missing something. I'll keep N here too. Okay. So now I will have map to store lost index. Okay. So if you have 2, you have to, this will be bit. Sounds from behind. I can't think about that, right? It's just a movie having extra things. So this is what we are trying to maintain in this one. Okay, one, lost index, right? So now we are at n, c in n. See, maybe this problem can be solved without O of n, without Fenwick tree. But then let's use this chance to learn Fenwick tree. Okay. So we will maintain, we'll try to form this thing. Okay, let's do one based indexing. Then I have to make it as n plus 1 here. I know we should not update templates like that, but okay, let's do one based indexing because initially everything is 0, right? So that's the reason why we are doing one based indexing. Okay, so now maybe there are better solutions, but I'm not doing them because I'm trying to explain Fenwick tree. Okay, what should we do? Let's just keep a of 0 equals to n or something. Bit of 0 equals to n. See, g of 0 is 0. I'm just using that. Or else we can just do add of 0 comma n. Let's say initially all values are at 0. All values are at 0. Let's just assume that. Now what do we do? Now what do we do? We have to remove this 1 from previous, and then we have to remove this 1, and then we have to make the new 2 as 1. We have to make this 0, we have to make this 1. So what do I do? Add of lost idx of a of I comma minus 1, lost idx of val equals to I, add of lost idx of val comma plus 1. What this does, this removes minus 1 here and then adds 1 here. Okay, now we have this. So now we have this array. Now we binary search to find the range for greater than or equals to k things. So int left equals to 0, let's say, right equals to I, let's say. K is 1, right? So I equals to I plus 1, let's say. While left not equals to right minus 1, int mid equals to left plus right by 2. So we have two things. This is 0 less than k. This is always greater than k. Okay. So let's try to find this being greater than or equals to k. Let's try to find less than k. This is less than k, right? Let's try to find less than k. Okay. If you find less than k, this is less than k, this is greater than or equals to k. Now, if sum of mid comma I greater than or equals to k, left equals to mid, else right equals to mid. So we have our new range, right? Let's say uh, KL, K plus 1L. Bad names. K, now we have L comma R. No, that's used already. Li comma Ri. This seems fine. So what happens is Ri is the first one that became, Ri is the first one that so now we have left equals to first lost index with greater than or equals to k values, k distinct, right? So I'll make Ri equals to left. Okay, Now we have RA equals to left. Now I will do again binary search. Left equals to 0, right equals to I plus 1, but this time I will find R plus K. If it is greater than K, then only I will do this. If it is equals to K, then I won't do that. So now we are here. Now left is greater than K, right is greater than or equals to K, right? So Li equals to right. Probably Li less than or equals to Ri will most of the time holds. Or what happens is when there is no K at all, both of them will become 0 comma 0. Okay, now we are here. Let's make it Li equals to maximum of Li comma L. Ri equals to, because now we are taking intersection, Ri comma R. C out, okay, int answer equals to, sorry, answer, total answer is what we have to find, right? See, we have done something, but then it's wrong. Because the ranges are supposed to be these two, not those two. C plus I plus 1 minus L, I plus 1 minus R. See, it's always good to maintain ranges in some other way. Here it was right, right? Here it was left, right? Maybe right plus 1. Maintaining right plus 1 is better, or right minus 1. Okay, maintaining left here is better. So we have left as L of I. Okay, leave it. Or I will add here if. So was this the issue? So this was the issue. Why? I don't know, but that was the issue. When there's no one around to be the one who makes you. So, guys, we've somehow accepted that. So now let me go over F and G quickly. Bro, what the fuck are you doing? Relhad. Hey, I know ordered such solution. I have told that long back too. So guys, now let me read F. Okay, Nezuko suddenly woke up on the number line at point zero and has H health points. She wants to reach point D. These questions are bad. Like we have very great questions on higher ratings. See, the problem I have solved yesterday, the problem I have solved. This one. This is a good problem, right? See the problem, good problem. You are given some query, you have to do within these things, you have an operation, you can think logically what I have to do. Okay, logically you have to think what you have to do. And then I used divide and conquer and then it was solved with some work. But think of see this question. See, these questions are bad because these are lower rating ones. If you go to higher ratings, you have nice questions. Okay, don't get disappointed because this question looks shitty. Okay, shitty in the sense we have to see it cannot get logically complex, but then being able to solve this is also needed because to solve these questions you need sometimes some a bit of difficult code, like not that difficult in terms of sometimes you have to apply more effort, so you can learn effort here, but then there are nicer problems in higher ratings too. Okay, problems in higher ratings are not like complete difficult and difficult weird algorithms. They are like some nice puzzles. Once it gets solved, it's solved, otherwise it's not solved. All problems are like that, right? There is a difference between getting the solution or not getting the solution, right? So it's like try all problems. Just because this looks complex doesn't mean you cannot understand this problem, right? Nezuko suddenly woke up on the Neverland points and has health H points. I have to sleep. I cannot do these questions. She wants. I will just explain overall F. That's what other PCDs do too. I won't code this. She wants to reach point D in one turn. She can do exactly one of the two things: rest in the shade and increase her current health by one. Move from her current position to explosion. So she can only move this side. She can stay on shade and increase her health. Point zero health H. She has to reach point D. Each movement decreases Nezuko's health. If the movement is the jth consecutive movement, her health will decrease by j. So if she's moving, -1, -2, -3, -4, like, and then stops, 0. As a result of a move, Nezuko drops to health 0 or below. She cannot make that move. Okay. Where is shade? Is shade everywhere? Where is shade? So shade. So what happens? What's the structure of the problem? What's the structure? This seems easy. I mean, previous one is also not that difficult. So move, rest, move, move, rest, rest, move. Okay. If you see the structure of the problem, here it happens minus 1. Okay, minus 1. Minus 2. And then minus 3. And then rest. Rest will make it plus 1. And then again from here minus 1, minus 2, and then again plus 1. So that's how it keeps happening. But then only during move we move forward, right? We must make exactly d moves, d movements, and number of operations should be minimized. So this is fixed, which means number of rests must be minimized, right? Number of rests must be minimized, correct? Can we say anything about moves and rest? Should we do all the rest in the beginning and then try to move? No, right? Because doing rest in middle helps us. It will make this value 0. Let me confirm how health decreases. Move from 0 to 1. Initial health h d equals to 4. Do you have viewers? I'll solve one problem and go. When there's no one around. So guys, let me understand the test case once, like one problem once, do not make any mistakes. Move from 0 to 1, decreases health by 1. Now she has 1 health at 6 points. Move from 1 to 2, decreases health by 2. Now she has 2 at 4 points. Move from 2 to 3, point 3 and health 1 point. Rest and restore 1 health point. Now she has moved. Okay, so what I have told was correct. These things are correct. Hello to Susu and come back. Is moving as much as possible better? Is think about this, is greedily moving better? We have to think of that. Okay, we should not go to code. Don't spoil it for me. Okay, but before binary search 2, let us see somewhere something. Can we get something? Let's try to see something. If you can say, okay, is moving always better? Number of rest, maybe we can binary search on number of rest, but still, let's try to think before. Okay, before trying binary search, let's try to say whatever the basic things we can say on the problem. Is moving as much as, is this better? Greedily. So you're moving, right? Can you bring this rest before? What happens if you have this rest and if you bring that before? What happens? Think what happens if you bring this rest. If you swap these two things, what happens? Uh, if you swap a move comma rest, what happens? What happens? You will have higher health. You will be able to do a move. If you swap rest comma move, what happens? Think of that thing once. If you swap rest comma move, when there's no one around to be the one that makes you cry. So here you had some, let's just see that one. Move comma rest. Let's say you had health H here. Okay. And then this move was some jet move, let's say. Here health will be, here health was H. And then here health will be H minus jet. And then here will be H minus jet plus 1. Right. This is our progress. But instead, if we have done rest comma move, now what would be the value? H plus 1. And then H. So if z is greater than 1, it's always resting is better. Resting is always better than moving. If you have rest already, so now you can bind research. Now you can bind research on rest, because all the rest you will do initially, and then you see if you can move. But then this seems wrong, right? This seems wrong. Why? Why is it wrong? This is wrong. This is wrong. Why? This value is 1, right? This value is 1. So now this argument has flaw, because now this 1 will get affect, now that 1 will affect this thing, that 1 will make it, this moves z value as 2. So this is wrong. This is obviously wrong. We all know why it's obviously wrong, right? Doing all the rest before is bad, because this is increasing much more. So what can we say? So what can we say? If you have two moves here, if you have two moves here, then it is bad. But then if you have, let's say you have rest here. If you have rest here, then okay, I'm not getting anything here. Let me try reading G. I cannot waste time. I have to sleep. I cannot fuck my sleep at all. Which streams that no one watches. This seems a good problem. I don't know. Because this sounds nice to me. Okay, this may be a good problem. Let's try this one. You guys can decide which is a good, I mean, even this may be a good problem. Maybe there is some brute, some greedy, some statement. Maybe you can make some statement and solve using that. That's it, probably. Okay, this is unnecessary complex because it's an easy problem. Maybe you can say something even obvious ones. I like this. I like to see exchange arguments, but this is not working, so I won't see. This is not my try. This was, I thought this works, so I tried writing it. Okay, I thought of it before writing that. So we have to minimize rest. How to use rest now? How to use rest? Keep going, keep going, keep going. Use rest. And then again keep going, keep going, keep going, and then again use rest. Is movement always better? Is movement always better is first question, right? Is this what about this? Is moving always better? What does this say? Rest comma move. Okay, you have rest comma move. Is move comma rest better? That's what it says, right? Because we are telling moving before is better whenever possible. Whenever possible, whenever it's possible to move. Okay, so you have h is greater than or equals to, this is like jet move, let's say, and then you're resting. So here it is h minus z, here it is h minus z plus 1. But now if you're resting, even this we cannot say. Leave it, guys, that's a difficult problem to me. This seems nice to me. Small statement, let me read this. In the ruthless world of blue lock, Bharat Sutta 3 is a trio selected to overthrow. There will be trios, right, in the anime. The reigning champions and lead the Japan U20 team to glory. I don't know those things. Itoshi has already secured his place as the first participant. The remaining two spots will be considered in the tough side B selection. I have only seen initial few episodes. To test the strategic abilities of the candidates, Burak, Burak Suta has posed the following challenge. You're given an array n called performance records and Q queries. Each query specifies a subarray L, or in this subarray you find all recorded values that occur strictly more than these number of times. If they are occurring strictly more than these things, there can only be three values, right? There can only be three values. Three most occurring values, right? At max. Why? Not even three. At max two. Why? What does it mean if it what does it mean? You have three. If you have three greater than or equals to this, means it is three times, this is nothing but floor division is coefficient, right? Plus 1. So all of them are greater than or equals to this, greater than or equals to this, greater than or equals to this, and then this is 3q plus 3, which is greater than 3q plus r, which is greater than length. Impossible. So you have at max two things. So you have two things that occur the most in this length, right? So if we know max occurring and max minus 1 occurring, we are done. But this seems like a shitty computation, right? This seems like a shitty computation. This is not that good. Are you guys following me? Yeah, bros. Good night. I won't solve all problems because I'm not getting views anyway. So I will also slack. So I will try to solve this problem. This seems nice to me. See, this solves the problem, but is it any good? I don't think this is good. So I'll try to find something nice. I think maintaining max and max minus one is difficult. Maybe finding max occurring is okay. Okay, 4.5 seconds. See, guys, finding something that occurs greater than half times is easy. You can use randomization. This is correct. This you can use randomization. Okay. I have a solution for this. See how I'm not able to solve this, but then I have already have a solution to this. See, if something occurs more than half times, you can keep randomly selecting it, and within 60 moves, you will definitely touch it. This is correct. Why? Probability of not touching is less than or equals to of not touching it is less than half, right? If you do 60 times, it's less than 1 by 2 power 60, right? So do you guys see this thing? This is nice. Why? If you have a value, you can count its frequency in range L comma R using binary search. If you store these indices for this value, I hope values are between 1 and n. Why the fuck are these problems like this? Why the fuck? Why should the values between these things? Why they can't be between 1 and n? The problem doesn't change, right? Why are they between these things? They can be between 1 and n, right? Why are they between these things? Even if they are between 1 and n, the problem doesn't change, right? See, this is bad way of formulating, I guess. We can try to see this should never happen on code forces. Should I maintain a map now because of that reason? Guys, I want to claim something now. So is this clear? Guys, is this clear? See, yeah, probably this may not be needed for G, but this is a great good idea that used multiple times. To find something like that, you do 60 times so that you will definitely find that. So we can find one max occurring one. But now we have two things. See, just because it's 3q, it's like three multiples or three things, I will try to look at 0 1 2 0 1 2 0 1 2 0 1 2. I will split them into the reminders. Okay, now I have this 0 indices. Okay, now I have this 1 indices, 1 based. I will split like that. can I claim that if v occurs more than 1 minute, I think 2 by 3 whole power n also reduces. Not as quick as 1 by 3. I thought of using some logic, but I think it's not needed. If v occurs more than 1 by 3 times, then not finding it at all. Not as quick as 1 by 2, but still it grows. It's like 3 by 2 power n, right? It grows exponentially. So we should find a small enough n, okay, that is less than or equals to 1 by 2 whole power 60. I think if you just find that n is 2 by 3, if you find that n, maybe 200 works, maybe 200 works, right? And then per query we do 200. Per query we do 200. I think we are good if you do per query 200. Why? 200 times this would work. Maybe 300 works. So let's just do 300 times. See, why is this not compiling? So these two are not equal, only then we are adding it. We are not outputting the length. Who is designing code forces rounds? Like code forces rounds always have the length before, right? Otherwise, the checker will be bad. So let's submit it. Light. I thought of giving a root response to side escorts. You need not break and just try. At at what test are you? I'll also use just 100 then. What the fuck is coordinate compression? Oh, is it renaming? Good luck, bro. Tomorrow, do well. This doesn't help. Why? They can keep on asking big queries itself, and then, and then we may fail, right? They can keep on asking big queries itself, and then we may fail. Leave it, guys. Shitty problem. This is also. I thought it's a good problem by seeing this, I thought it's constructive, but then it's bad one. Let me read this one. This one seems good. Let me solve C. Okay. You're given an array of length n and a number k. Okay. In one operation, you can choose any index and set AI to any integer value x in the range 0, comma n. We can set something to anything, it seems. Okay. Find the minimum number of operations required to satisfy max of this array equals to k. We have to make max equals to this one. Okay. Minimum number of operations needed. So if that element is there, k should disappear. Okay. What should we do? K should disappear 0, 1, 2 up to so on, k minus 1, all must appear at least once. Because size is n, this is always possible, right? So for all k, okay, some didn't appear, must be removed, must be updated. Some x didn't appear, let's say, must be updated with an operation. For all k, must be removed with an operation, right? So I think we can make this k into all these k's, we can make them into 1, 2, 3, whatever these x's that didn't appear, and then if there are something else is left, then we will do that. So first x minus equals to min of x comma k, k minus equals to min of x comma k, and then answer is x plus k plus min of x comma k, right? Or minus 2 times min of x comma k, minus 1 times min of x comma k. Okay, have to do these many, but whatever is minimum, you can just cover them. Okay, you can just cover them. Done. If it is not 0, then what do we do? uh, am I right? This is a simple problem, just stating that all of them must be changed, all of them must be changed, maybe something can help each other. Done. This is not that difficult. What about other things? What about A and B? How is it a bit more difficult? Consider a string of in one operation. We have an operation. Choose position, swap the neighboring characters. You need to perform minimum number of operations. All characters are located strictly together, forming exactly one contiguous block. Wait, isn't this ChatGPT-able? Isn't this just sorting? Isn't this like number of inversions? So you have two possibilities: make all A's and then make all B's, or make all B's and then make all A's, right? So it's like number of inversions, like 1, 2, 3. Huh? Okay, this is already in its position. So one inversion. So it's number of inversions, guys, number of inversions. But we have only two things, right? So number of inversions can be counted in a better way, probably. It's in general it's number of inversions, but maybe we can do, because it's a due to b, maybe we can index, we can just use the fact that first a comes here, first b goes there. Okay, we can just use that. In each swap, indexes of sum of position of indices of a changes by -1, right? Summation of positions of a will change by -1, right? So that's it. I will use that instead of number of inversions. I will use the fact that see a b, two values, right? In each operation of swapping b comma a, we get a comma b. So sum of index of a reduced by 1. If you guys have seen my invariance video, you could have gotten this one very easily. Okay, what happened after one operation? S index got 1, right? So sum of indices of A got 1, reduced by 1, right? So if you have seen my videos, you could have gotten this very easily. Now uh, I want, I know final indices, right? I know final indices, which are, what are final indices? 1, 2 up to so on, right? Final indices are 1, 2 up to so on, count of A. Initial indices is this. Difference would be the answer. So I will get sum of A, sum of B, count of A, count of B. Okay. String as seen as for int I equals to 0, I less than n, I plus plus, if s of I equals to a, sa plus equals to I, ca plus plus, else s of b plus equals to I, cb plus plus. Now answer is bringing s to the front. What is bringing s to the front? Sa times I, ca times ca plus 1 by 2. Bringing b's to the first. What is bringing b's to the first? Sb times cb times cb plus 1 by 2. This works only because there are only two elements. If it is more, it's about inversions, but here it's not about, it need not be about inversions. Even inversions equal to this value, but it need not be about inversions here. Okay, or I could have just made it -1 here. How is two operations correct here? This is wrong, right? Okay, did I understand the question wrong? Okay, this is a different problem. We only want, okay, something should occur together. Something should occur together. For something to occur together, notice that gaps between s must come to 0. and in one operation it can only reduce by 1. So it's the lower bound, and it's good enough. So it's like gaps between adjacent s. Okay, it's like gaps between adjacent s. So let's say lost a equals to -1, lost b equals to -1. Okay, int pos a equals to 0, pos b equals to 0. If la equals to -1, la equals to I. If lb equals to -1, lb equals to I. We don't need this. We don't need this. Pos a equals to I minus lost index of a. Pos b equals to I minus lost index of b. Now LA equals to I. LB equals to I. Answer equals to minimum of pos A comma pos B. C out. Answer done. Wait, this is also wrong. This is also wrong. In one operation, this is also wrong. It depends on first LA. Okay, depends on whatever is the minimum LA. Okay, it depends on minimum LA. So what do we have to do is, guys, I have solved this problem. I have solved this problem. Yeah. See, I have solved this problem once in my problem solving stream. Uh, if you go here, 1 minute. I know the problem, but then it's about, see, in between b's, you have a, you have a, you have a, you have a. In between b's, either escape to front, left side, or right side. Right? They either escape to left side or right side. Okay. They either escape to left side or right side. I have solved this problem for much more complex case. Problem solving only it is problem solving. But then I have solved this problem for much more complex case, I guess. I don't remember. The diagram should be something else. See, now anything that is going to left, it crosses s in between, right? So for this one, it crosses 2s. If it was here, it crosses 3s. So for these things, it's about minimum of number of s on either sides. Okay, It's minimum of number of a's on either sides. So if you know number of a's on this side, minimum of number of a's on either sides, right? Now it is. So how do we find that? Like now, number of a's before this, number of a's before this. If I know number of a's, I think if I know number of b's before this, before every a, then I can do this. Okay, I will find number of b's before every a. See, it's about these bees will escape from this side. These bees will get weight 1. These bees will get weight 2. These bees will get weight 1. These bees will get weight 2. Middle ones will get any of that. Both are same. So bees dot pushback of CB CA plus plus else S dot pushback of CB CA CB plus plus. So now we have number of B's before this. We have to start from I equals to 1, I less than int size of A is equals to count of S, let's say. For each A we are adding this value, right? So then SA I plus plus. Okay. SA plus equals, sorry, pos A plus equals to b's of I, whatever the b's in between size, times minimum of I comma SA minus I. You have I things before, you have SA minus I things after, whatever is minimum. Int SB equals to S dot size of so this would work. This one escapes like this. This one escapes like this. This minus one. Okay. No, you have I number of ones on this side. You have remaining ones on this side, right? I will end the stream after this video, guys. I don't even know if anyone's watching my videos. 1 and 2. Okay. Whenever an A comes, let's reset CB to 0. Whenever a B comes, let's reset CA to 0. Why did I do this? Why did I do this? I don't know, leave it. Someone has told me just having B is enough. Accepted. So we struggled on D a bit. Let me do B and that, and then I'll leave. Petya has an array of n integers. It is known that n is even. Petya must divide the participants into exactly this many. Each pair is my video there. I didn't get this, Pradeep KR. So let me uh, read BC. I will quickly do and then I'll sleep. I can't do much. BC I will do and then sleep. BA. Petya must divide the participants into exactly each index must be included in no more than one pair. For a pair, the difference is defined as Petya wants to conform such that the maximum difference among all pairs is minimized. Such that the maximum difference among all pairs is minimized. How can we prove this? Wait, someone asked me how can we prove something in which contest? That was yesterday. Okay, that was yesterday. I think we can prove it in some way. Is it like is it like keeping you guys can think of extreme cases. Okay, let's say half people are here, half people are here. Okay, now you have to match the first guy to this guy, first guy here, first next guy to next guy here after sorting. Why? Anything else you do, let's say this difference between all of the perfect pairing is D. Anything else you do will make greater than D, right? So that is the minimum maximum difference. But how do we prove that? Is that a lower bound? Uh, Wait a minute. If all of them were even and all of these were even, you can just pair like this, you can pair like that too, right? Then it will all be, then it will all will be zero. Okay, it's all about pairing adjacent things. Sort, pair first to, pair next to, pair next to, pair next to, and so on. Now, okay, that's it. Because this will be a lower bound, right? This will be a lower bound. Why? Why will this be a lower bound? Hmm. I had to think. Okay, that's an easy guess. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 9, 10 up to so on. Okay, why this will be a lower bound is there are odd number of things on this side. There are odd number of things on this side. So there must be a pairing from here to here. See how beautiful the proof is. Guys, guys, you see that? See Pradeep KR, you're telling after sorting obvious, but see my explanation. See, we have this pairing, but how do you say that's the minimum pairing? How do you say like that's the minimum value? You have to show that's a lower bound, right? You have to show that's a lower bound. So what I mean is maybe you have something like this. uh, Maybe you have something like this. Okay, you have this big, and then this is, sorry, you have this big, and then you have this small, and then you have this big, and then you have this small, and then you have this big. But then we have to take first two, we have to take these two, we have to take these two. So now ma- how can you show that this is a lower bound? How can you show that this is a lower bound? How can you show that this is a lower bound? You have guessed it, but then unless you show that this is a lower bound, you cannot prove that there cannot be a better answer, right? But how can I prove that this is a lower bound? If I draw a line here, okay, there are odd number of things on this side and odd number of things on this side, so there must be something pairing from this side to this side that gives me this as a lower bound. So now these things are lower bounds, so maximum among them is a lower bound and an answer is possible with that. So that, see, I say you guys to prove things, right? So if you're proving things on easy problems like division 3b, your logical abilities will improve. Your uh, and then you will look for lower bounds in a difficult problems. Do you see the difference, Pradeep KR? You told after sorting obvious, but then I told there is a lower bound. I mean, we have to show that it's a lower bound, and then I split them into two things, like I cut odd number of things, odd number of things. There must be a pair from here to here, so that's a lower bound. See, after getting proving things is easy. You are trying to see. I got the answer in the same way. After getting answer, you have to show that this is a lower bound. Now, at least this much should be done, and you can do this. So that's an answer. So that's done. All of them are lower bounds. Okay, so maximum of them could be done. See the difference. Like, try to learn from me. Just because the problem is solved, see, if it was someone else's PCD, what they would do is sort, take this, done, accepted. If you say this thing 1 2 9 10, here it's maximum happening, but then someone may question, why not pair these two? So looks like it's reducing, right? But then our answer has this lower bound, and this is possible. That's why we are done. See how I am solving in a better way, even though it's an easy problem. It's about looking lower bounds because you have to prove that it's minimum. I think this is much better problem than other problems like C or F or G. I don't know what F is F, E. Those were not that good, right? I didn't feel that good because what we are doing there was brute force, but here I had to prove that that's minimum. All these are lower bounds, so maximum among them is a lower bound, and then answer is possible with this. So done. It's all about finding lower bounds, guys. So can anyone might have approached this in this way? Okay, if I split them into odd things, this length is a lower bound. So maximum among this is an answer, and then coming to, okay, can I try to see with these lengths being possible? Okay, see guys, it's it's like two different ways. Yeah, it's like, no, what I'm trying to say is there are two different ways. Whenever you want minimum, you have all possibilities that give you an upper bound. Okay, all possibilities will give you an upper bound. Because of that reason, you guys will try for random possibilities. But yeah, I got it. But no, what I'm trying to say is all possibilities will give you upper bounds. Answer is even better. Answer is even better. Answer is even better. But lower bounds are the things that proves that answer is at least this much. Answer is at least this much. And if you're proving that this is minimum, that means you're showing a lower bound. You're showing that this is a lower bound. So if you think intuitively, people come from possibilities and then try to reduce that. But then if you see that we're proving, we are finding lower bounds. We are coming from this side actually. So what happens is, in difficult problems, let's say much difficult problem, you have to find you can try for lower bounds. Sometimes you can try for lower bounds. Sometimes doing that would be easier than doing this. Sometimes, but then I had to sleep. After doing all of that, what did I achieve? What did I achieve? What are necessary conditions? no zeros, even number of minus ones, right? That's it. So no zeros, even number of minus ones. All if minus ones are odd, make it two operations, and then all zeros. That's it. So these are the necessary conditions, right? You cannot keep that minus one. You cannot keep these zeros. You just have to keep update them. Guys, good night, guys. I'm ending the stream. Good night, guys. I'm sleeping.